Hi guys, it's Kate. This video is a quick look at what we discussed in section on the average rate of change of a function, and it's going to tie in some of the representations of functions that we've been talking about in class, specifically the graphical representation of a function. But I'm getting ahead of myself. Let's recap first. What we talked about in class was how to determine the average rate of change of a particular function. In our opening example, we discussed this function f, which gave as output the distance traveled into a car trip. So here's a basic idea of what that function does. It takes some number of hours, x, into the car trip, and then it spits out as its output the distance traveled. And in class, we discussed how to compute the average speed over various time intervals. We talked about how to figure out the average speed over the first 3 hours. And we agreed on this expression. That numerator, f of 3 minus f of 0, takes the distance traveled 3 hours into the trip minus f of 0, the distance traveled 0 hours into the trip, and divides it by 3, the number of hours that have elapsed. We talked about what the average speed would be the next 3 hours of the trip. And we agreed that if we took the distance traveled 6 hours into the trip, subtracted off the distance traveled 3 hours into the trip, we would capture the exact distance traveled during those 3 hours and divide it by the amount of time that had elapsed. And that would give us our average speed over that time interval. And so when we go to generalize something like this, and we're saying, hey, we have this function, we want to know the average rate of change of the function over a particular interval. And let's clearly state what we're doing here. We're trying to find a general way to express the average rate of change for some function f over some arbitrary interval, we'll say from a to b. In this first example here, a to b was 0 to 3. In the second example here, the interval would be 3 to 6. So when we're trying to talk about this in the general case, we're looking for, okay, how do we express the average rate of change of some function f on the interval from a to b? We can generalize from our specific examples up here to the general example, right? We want to take the difference in the function values, meaning f of b, and subtract off f of a, just like we had taken f of 3 and subtracted off f of 0, or f of 6 and subtracted off f of 3. And then we want to divide by the length of the interval. Now in this particular example, that length was 3. It was because the length of the original interval, all those x values were timestamps, that ended up being significant. We were dividing by 3 hours. We were saying we've traveled this distance over 3 hours. And you now want to generalize from that. So how to find the length of an interval? Well, here the interval was 0 to 3. Here the interval was 3 to 6. The quick, straightforward way to do that is to take the end of the interval here and subtract off the beginning of the interval here. So we have f of b minus f of a over b minus a. So this is the generalization of the two specific, and we did a lot more examples than this in class, but the two specific examples that we just briefly looked at in this video. We are looking in the numerator at how much the function changes as you go from a to b, and then we're dividing that by the length of that interval. And so this measurement that comes out is the average rate of change. It says if f changed in a constant way, at what rate would it have to change in order to achieve this difference in the function values over this interval? Now, I want to say one moment, what does this mean in terms of a graphical representation of a function? Does the average rate of change have any particular significance? Well, we've talked about what the algebraic expression is, so let's take a look at the graphical representation of a function and draw any function f in front of you. It can look like anything. Now I'm going to demarcate an interval on here, meaning I'm going to mark out, here's like an A, and here is a B. And so where would I sort of visualize the average rate of change here? Well, what's interesting is that you may notice that the point on this function right here and right here, write those 2 points, the coordinates of those 2 points. Well, the x value for this point is a, and the y value, because it's on the function f, is f of a. The x value for this point is b, and the y value, because it's on the function f, is f of b. Now take a look at average rate of change. Now graphically visualizing where a and f of a and b comma f of b are with relation to each other, what significance does this expression have in this graphical representation? Well, you might notice that f of b minus f of a, that's the difference in the y values between these 2 points, or the quote-unquote rise. What is b minus a? Well, that's the difference in the x values between these 2 points, or maybe quote-unquote the run. And so I think I've sort of led you to understand that what you're looking at is rise over run for a line that goes through these 2 points. Interesting. So when we're looking at this line, if we draw it in there, connecting the 2 points, what we've done is we've created a secant line. That's what this is called. It connects 2 points on a function, and the slope of that secant line is the average rate of change over that interval. So the slope of the secant line is a great way to visualize the average rate of change on the interval from A to B. So that is a really cool result. Not only do you want to feel comfortable with the algebraic representation of a function and therefore the algebraic representation of the average rate of change, that's this in the general form. So that's how you would express the average rate of change of some function f over the interval from A to B. But you also want to think about what it would look like graphically. You would find the point at x equals a, the point at x equals b, join the two with what we've now named a secant line, and realize that the slope here, rise over run, which would be the difference in the function values over the difference in the input values, that's the average rate of change. So the slope of the secant line is a great way to visualize the average rate of change when you're looking at a graphical representation of a function. One thing that's pretty cool is this actually helps better define our definition of concavity. Note that in this particular case, our function is concave up. This secant line lies above the function on the interval if it's concave up on that interval, whereas if it were concave down, let me try to draw that in, the secant line would lie below the function if it were concave down on the interval. So that's another way to define concavity, but that is a separate conversation that we'll be fleshing out even more as we continue on into our discussion of rates of change and how they work alongside functions. Hope this helps. If you have any questions at all, please don't hesitate to ask.